In 12 days, a 3 billion-ton interstellar visitor called Atlas will plunge past our star at 80 times the speed of a bullet, and that's where things could go wrong. Its path is nearly aligned with the solar system plane, something no random comet should do, raising the disturbing question: is this a natural wanderer or a machine designed to break at our star and stop within our solar system? While Earth's eyes will be blinded by our star itself, the only thing we'll know for certain is what emerges on the other side. The real danger lies in what we won't see when it matters most. A path that defies the odds. Atlas rockets toward our star at nearly 55 kilometers per second, following a path that defies probability, like a car entering perfectly into the right lane of a cosmic highway. Instead of diving from a steep, random angle, it glides through the solar system plane tilted just 5 degrees from the ecliptic, the invisible disk where planets orbit like a spinning coin in the air. For an interstellar space visitor, this is a statistical outlier. Random arrivals should spread across the sky, most missing the ecliptic by wide margins like balls thrown from all directions. Yet here, the trajectory nearly overlaps the planetary lanes as if mapped to blend with local traffic, like a driver who perfectly knows the traffic rules of a foreign city. Orbital simulations by planetary scientists show that only a minuscule fraction of interstellar objects should arrive this way. The ecliptic covers a thin slice of the celestial sphere. For a comet to approach within 5 degrees is like throwing a dart at a spinning globe and hitting a city street. Technically possible, but statistically nearly impossible. The last 2 interstellar objects, Oumuamua and Borisov, came from high inclinations, their paths cutting through the solar system at sharp angles, like planes flying too high or too low. Atlas, in contrast, traces a retrograde arc moving against the planetary current, but nearly flat along the disk, like swimming against the current but at the water's surface. This alignment isn't just a curiosity. It changes what's possible at perihelion, the closest point to our star. An object approaching along the ecliptic meets our star at a shallow angle, maximizing the window for any maneuver that leverages solar gravity like a skateboarder using a ramp to gain extra speed. If a spacecraft designer wanted to use the Oberth effect, a way to amplify a rocket burn by timing it for maximum speed near our star, this is the geometry they would choose. But the numbers alone are enough to raise eyebrows. Discovered on July 1st, 2025 by the Atlas survey in Chile, Atlas is only the 3rd confirmed interstellar object. Its entry velocity of over 200,000 kilometers per hour confirms it's not bound to our star like a visitor who clearly isn't from the neighborhood. Perihelion comes on October 29th, 2025, at a distance of 1.36 astronomical units just inside Mars's orbit, like passing between 2 moving cars on a highway. For now, orbital mechanics says it should slingshot and disappear forever. However, the strange alignment of the trajectory with the ecliptic, along with its hyperbolic velocity, leaves a persistent question. Is this cosmic chance or the signature of intention? As the clock counts down to perihelion, the stakes rise. If Atlas is natural, it's a rare but explainable visitor. If not, the geometry alone suggests a level of planning and purpose that goes far beyond chance. The moment of truth. Oberth effect. At perihelion, Atlas will be moving at nearly 68 kilometers per second, more than double the speed of the fastest spacecraft ever launched from Earth, like a cosmic cannonball. This is the moment when the laws of orbital mechanics offer a unique loophole. The Oberth effect, first described by Hermann Oberth in 1929, states that a rocket burn is much more effective when performed at high speed within a gravitational well. Simply put, the same push from a rocket engine does much more when the object is moving faster, especially near a massive body like our star, like hammering with full force, instead of just tapping. The principle can be summarized in a simple rule. The change in orbital energy from a burn is proportional to the object's velocity at the moment of the burn. If a spacecraft fires its engines while crawling through deep space, it gets only a modest energy boost, like pushing a parked car. But fire those same engines while passing our star at 68 kilometers per second, and the effect multiplies, like pushing a car that's already moving at high speed. A 1 kilometer per second change in velocity at that speed translates to a dramatic alteration of the object's trajectory. The math is clear. Kinetic energy increases with the square of velocity. So a burn at perihelion is like swinging a hammer with full force, not just gently tapping. For Atlas, the theoretical path to capture would require deceleration, what engineers call a retrograde burn, right at closest approach. The goal would be to lose enough velocity to change from a hyperbolic escape trajectory to a closed orbit bound around our star, like braking a high-speed car to enter a parking space. Calculations show that to fall into a permanent solar orbit at 1.36 astronomical units, the object would need to lose about 20 kilometers per second at perihelion. That's a huge ask. Even for the most efficient chemical or nuclear propulsion known, the amount of fuel required would approach the object's own mass, like a car that needs to carry its own weight in gasoline. However, the Oberth effect is the only way to make such a maneuver remotely plausible with any known technology. Natural comets experience outgassing jets of vapor and dust that can nudge their paths. But these forces are weak, chaotic, and rarely aligned with orbital needs. They might change a comet's velocity by a few meters per second, not tens of kilometers, like the difference between being pushed by a breeze versus a hurricane. A controlled, precisely timed retrograde burn at perihelion would stand out in the data. The resulting change in trajectory would be obvious to astronomers tracking its path after solar conjunction. The telltale sign, a sudden step-like drop in exit velocity far beyond what outgassing can explain, like a car that suddenly slows down for no apparent reason. That's why the perihelion window matters. If Atlas attempted deceleration, our star's gravity would act as the amplifier, turning a modest push into a major transformation. The mechanics are straightforward, the energy stakes immense. What remains is watching for any sign that nature or something else has the means and intention to use them. The Great Blackout. From mid-October through early November 2025, Atlas disappears behind our star. From Earth's perspective, like an actor exiting stage at the most important moment of the play. This isn't a stroke of bad luck. It's the result of a fixed rule in astronomical observation, like a law of physics that can't be broken. When a target falls below about 30 degrees from our star, all major ground-based telescopes are forced to look away, like being unable to stare directly into a spotlight. Avoiding our star isn't just about protecting sensitive optics from blinding light. It's a safety protocol built into hardware and software like automatic brakes in a car. The blackout window extending from October 22nd to November 7th means that as Atlas races through perihelion, no direct images or spectra can be collected from Earth. Space observatories face the same limits. The Hubble and James Webb telescopes are programmed to never point within 50 to 85 degrees of our star, eliminating any chance of a last-minute peek. Even TESS, with its wide-field cameras, is blocked by solar elongation rules, like having to close your eyes when the light is too bright. The Parker Solar Probe and Solar Orbiter, both designed for close solar studies, are pointed at our star and rarely risk deviating off-axis for cometary science. Their instruments are optimized for plasma and magnetic fields, not faint objects at the edge of their fields of view like using a microscope to try to see the moon. Mars orbiters, briefly better positioned, attempted risky snapshots as Atlas grazed past in early October, but the object was 50,000 times fainter than their usual targets. Preliminary images from the ExoMars Trace Gas Orbiter were dismissed by the ESA team as likely noise, like trying to photograph a candle in a snowstorm. No confirmed detections were released. For now, the only certainty is absence, like trying to watch a movie with the screen turned off. A multi-week period when any dramatic change, natural or otherwise, could occur unobserved. When the object reappears near dawn in November, astronomers will be looking for after-the-fact evidence, piecing together what happened in the dark, the phantom mass mystery. Brightness should be an indicator of mass. For Atlas, that assumption is now under fire, like discovering that a person who looks large actually weighs nothing. Photometric readings calibrated against standard comet reflectivity place the object's mass at about 33 billion tons, a number that would make it one of the heaviest natural visitors in recent memory. However, when planetary dynamicists ran the numbers after the Mars flyby on October 3rd, the result was silence, like throwing a stone into a lake and seeing no ripples. At a distance of just 29 million kilometers, a body of that size should have nudged Mars's orbit, or at least appeared as a small anomaly in orbiter navigation data. Instead, the Mars Reconnaissance Orbiter and ESA's Trace Gas Orbiter reported no measurable perturbation, like a giant truck passing without making the ground shake. Deep Space Network tracking records showed nothing above background noise, like listening for a whisper in a quiet room and hearing nothing. This isn't just a matter of missed signals. In 2014, comet sighting springs much closer passed by Mars left a detectable fingerprint on the planet's trajectory. Even being smaller and lighter than Atlas should be, here, with an estimated mass orders of magnitude larger, the effect is completely absent, like a ghost that leaves no footprints. The discrepancy hasn't gone unnoticed. Astronautics teams have double-checked orbital solutions, searching for any unexplained drift in Mars's motion or spacecraft signal timing. The answer remains the same: no gravitational tug, no residuals, no evidence of a massive solid core like a balloon that looks heavy but is filled with air. Some suggest the mass is simply overestimated, that Atlas's brightness could be inflated by dust or an unusually reflective surface, like a person wearing clothes that make them look bigger. Others point to the possibility of a hollow or highly porous structure, a cosmic shell rather than a rock, like a ping pong ball instead of a bowling ball. The rotation rate measured from periodic brightness changes suggests a body spinning faster than a solid chunk of that size should allow like a top spinning too fast to be made of iron. For now, the numbers refuse to add up. A bright, fast-spinning object with negligible gravity, an equation that points to a hollow shell, whether built by nature or something else. The telltale chemistry. Spectroscopists tracking Atlas in mid-September recorded a coma extending 180,000 kilometers, an envelope of gas and dust that dwarfs the nucleus itself, like a cloud the size of a small country. The dominant molecule in these measurements is hydrogen cyanide, released at a rate of 5 times 10 to the 25th power molecules per second. That's about 2 kilograms of HCN vented into space every second, like a constant leak of poisonous gas. But in the vacuum of space, a number that stands out among known comets, but isn't without precedent, like finding a very tall person, but not impossible. The sheer size of the coma and steady cyanide production suggest active outgassing driven by sunlight heating ancient ices. As Atlas approaches the inner solar system, jets of vapor and dust flow outward, sculpted by radiation pressure and solar wind, forming an asymmetric halo that signals motion and volatility. However, the chemistry is more than a curiosity. It's the baseline for how a natural comet should look before perihelion, like a chemical fingerprint. The presence of HCN, along with traces of water and carbon monoxide, anchors Atlas in familiar solar system comet territory. Spectral signatures match those cataloged in previous interstellar visitors, though proportions and intensities suggest a unique formation history, like a familiar recipe with slightly different proportions. For now, the coma's behavior supports a natural explanation, a volatile, rich, porous body shedding mass as it approaches our star like ice melting in heat. This baseline, measured before the critical solar encounter, will become the reference against which any post-perihelion changes are judged. If chemistry shifts or the coma fragments in unexpected ways, those deviations will stand out against the spectroscopist's careful September record, like false notes in a symphony. The hollow shell scenario. A hollow shell racing toward our star is more than a physical puzzle. It's a scenario with testable consequences, like an experiment that can be proven or disproven. Imagine a structure built not to endure, but to unfold. At perihelion, when sunlight and gravity are at their fiercest, a fragile body could naturally fragment, scattering debris in random directions. However, there's another possibility, one that scientists like Avi Loeb are determined to keep on the table: intentional deployment, like a flower opening its petals at the right moment. If Atlas is designed, perihelion offers a unique moment for action. Instead of chaotic breakup, the shell could release smaller units, probes, or sensors, each with its own trajectory. Like dandelion seeds catching a gust of wind, in this case, the evidence would be concrete. Post-perihelion, astronomers would look for discrete, non-random trails radiating from the original path, like fireworks that explode in specific patterns. Some fragments accelerating or steering away from our star, not drifting passively. Patterns in the debris field, straight lines, sudden velocity changes, or clusters moving as if under control would stand out against the backdrop of natural chaos. Loeb's Galileo project is preparing for exactly this test. His checklist is clear: track every outbound fragment, measure velocities, compare against natural comet breakup models. If data shows randomness, the design scenario vanishes. But if the sky reveals order, the implications are profound, like finding organized footprints instead of random tracks. The days after perihelion will decide which story the evidence supports. The lost images from Mars. The ExoMars Trace Gas Orbiter, built to scan the Martian surface, was pressed into service as Atlas passed Mars in early October, like using a microscope to try to see stars. The instrument team turned their high-resolution camera from the planet to black space, capturing a series of 5-second exposures, each stretched to the technical limit. The target was nearly 50,000 times fainter than anything the orbiter was designed to image, like trying to photograph a candle from miles away. Raw frames showed little more than a scatter of digital static. In most, the supposed comet was indistinguishable from background noise, like looking for a needle in a haystack of pixels. Processing pipelines tuned for sharp Martian terrain struggled to extract any reliable signal, like trying to use a coffee filter to sift sand. Analysts at the European Space Agency flagged the preliminary images as likely noise, not confident enough to claim even a weak detection. The challenge wasn't just faintness. Mars orbiters relay data back to Earth in tight windows, competing with planetary science priorities and downlink bottlenecks. Each batch of images passed through layers of calibration, compression, and review before reaching public archives, like a letter passing through many hands before reaching the recipient. With the object so close to our star from Earth's perspective, there was no way to verify these ambiguous frames against ground-based observations. By the time any processed data became public, scheduled for late November, weeks had passed since perihelion. In that gap, any sudden change in Atlas's trajectory or structure could go unnoticed, like missing the most important moment of a movie because you were in the bathroom. For analysts, each ambiguous pixel was a reminder. The most critical moment might be hidden in noise, and the only clues could arrive too late to capture in real time. The implications of capture: a body from interstellar space captured by our star would rewrite the rules of planetary science, like discovering a new law of physics. For researchers, it would mean the first permanent sample of extrasolar material, an object to study for generations, like having a piece of another world in our backyard. For defense planners, the scenario is less academic. Internal memos circulating at NASA and the US Space Force during the blackout window outlined contingency models. If a designed object used a perihelion burn to shed velocity, surveillance protocols would escalate, like increasing security when there's a potential threat. No agency has released public guidance or threat assessments, but the existence of those drafts, even in redacted form, signals a shift in how such arrivals are modeled. A single headline about capture or probe deployment could trigger sentiment shocks far beyond the scientific community, like a panic that spreads faster than the news. However, for all speculation, evidence remains king. To judge extraordinary claims, observers need a clear checklist. First, watch for a sudden change in exit velocity, an abrupt drop visible in astrometric residuals that can't be explained by cometary outgassing. Next, look for organized debris, discrete trails or fragments accelerating in non-random directions, not the chaotic spray of natural breakup. Cross-reference with atmospheric anomaly records, especially UAP-type event reports, synchronized to perihelion like connecting dots in a puzzle. The datasets to watch are public ground and space-based optical and radar observations, polarization studies, and citizen science occultation campaigns in the Southern Hemisphere. Archive channels from NASA, ESA, CNSA, and the Galileo project will release recovery images, trajectory solutions, and raw sensor data in November and December. Falsifiability is the rule. If the exit path shows no step change, if fragments drift randomly, if no correlated anomalies appear, the story returns to nature. The test isn't what's possible, but what the data confirms, like a detective who needs evidence, not just theories. The verifiable fact. On October 29th, 2025, Atlas will reach perihelion at 1.36 astronomical units from our star, a fact verified by both Atlas survey records and NASA trajectory data. Its near ecliptic approach of 5 degrees is statistically rare for interstellar objects, as confirmed by orbital models, like winning the lottery, possible but unlikely. While photometric readings estimate a mass of 33 billion tons, the October 3rd Mars flyby produced no detectable gravitational effect, an inconsistency documented in ESA and NASA navigation records. Imaging gaps during superior conjunction blackout are a matter of published telescope schedules, leaving a critical window unobserved, like having to close your eyes at the most important moment. So far, no classified defense advisories or market alerts have been released about the object's potential capture or artificial origin. Whether Atlas is a porous comet or something designed, only post-perihelion debris patterns and velocity changes expected in late November, datasets will offer answers like waiting for the results of a crucial medical exam. For now, the evidence highlights both the limits of current observation and Atlas's extraordinary nature, like having almost all the pieces of a puzzle, but still not being able to see the complete picture. Its next move remains a matter of record, not speculation, like watching a movie where the ending hasn't been written yet, but will be revealed in real time. The countdown continues, and in a few weeks, we'll know if we're witnessing the strangest comet in history or something that will forever change our understanding of what's possible in the universe. The silence of space has never been so loud, and the answer has never been so close.